Let's start question number 2. Write the algorithm of flowchart for the following task and complete the table. Here is given tables and three different operations we have to perform on this table, and we have to give the final result and the error message of the table. So let's start with the subtraction. Here we start with the subtraction. Remember that this value I am taking n1. This can also be written as 0.5452 into 10 raised to the power minus 99. So this can also be written like this. So in the process of subtracting, do remember that. Coming back to the question, given subtraction, for the first case we perform n1 minus n2. In this, the error will show underflow. The error will show underflow because the computer cannot store this much small value. It is approx 10 to the power minus 99. Which is a very small value. So computer cannot store this much small value. Therefore, the message will be underflow. Next, we have subtraction only. We have to perform subtraction on these two, and the answer will be this. And this is the normal. This can be stored in the memory, so there will be no error message. Now coming back to the multiplication, here is given multiplication. The answer we have seen, this message will be underflow. Coming back to the multiplication, we have two operations on multiplications also, first and second. For the first multiplication, the answer would be 0.4932 e 200, and this will be 10 raised to the power 200, which is a huge value, and we cannot store this value in a computer, so the message will be overflow. Now comes the another multiplication operation here. Here the multiplication operation on 0.1111 e10 and 2 equals to 0.1234 e15, and we have to perform the multiplication operation on that, and the answer would be this. So it has created a loss of 0.974. Now coming on the division, we have given the division methods also. n1 divided by n2 will result in this, and e to the power 100 is a huge value, therefore message will be overflow. Now 0.9998 e raised to the power 5 and 0.1000 e raised to the power 98 will result in this, and minus 103 is the smallest, very small value, so we cannot store this much small value, so the message will be underflow. So this all thing will be given filled in the table here, and the table will be completed. This was the question number 2. Come to the question number 3. Verify the associative law and distributive law of arithmetic with fitting 4 Mantissa digit and providing the correct answer if number is truncated. So this is the associative and this is distributive. If this and this is true, then we have to check for the truncated property, and if this and this is the false, we don't have to check for the truncated property. So let's go. A, B and C values are given here. A, the property is A plus B minus C and A minus C plus C. So we have to check for both LHS and RHS. First we will check A plus B minus C. So here A plus B value will be 0.5720 even, and A plus B minus C will be 0.7600 even, E minus 1. Now checking for the RHS value will be A minus C will be 0.2121 even minus, and for A minus C plus B will be the value 0.7656 E minus 1. Hence these two values are not equal. LHS are not, RHS are not given. It doesn't go associative property. So it doesn't go associative property. Similarly, this will not go under the distributive property. What was the distributive property? We have seen here, sorry. The distributive property is A B minus C equals to AB minus AC. This is our distributive property. For checking distributive property, B minus C is this, A B minus C value goes to this. After checking RHS, the value comes AB minus AC is this. Both the values are not same, hence it is not distributive. So we don't have to check for the truncate. So this was the question number 3. Question number 4, true and false. First question, the number of arithmetic operations, minimize the number of arithmetic operations whenever possible. There are several benefits to minimize the number of arithmetic operations whenever possible. The first benefit is efficiency. We can improve efficiency by reducing the processing time, and we can do this by minimizing the number of operations. Second is accuracy. Each arithmetic operation introduces a certain degree of error, which can accumulate over multiple operations. By minimizing the number of operations, we can reduce overall error and improve the accuracy of the result. Robustness. The arithmetic operation can also lead to the numerical instability and divergence, especially when dealing with a large number or small values. By minimizing the number of operations, we can reduce the risk of numerical instability and make our algorithm more robust. Memory usage. Each arithmetic operation is required to store space in memory. By minimizing the number of operations, we can also reduce the memory usage and optimize the available resources. So by minimizing the number of arithmetic operations, we can have several benefits like efficiency, reduce in processing time, accuracy, accurate result will be there, less error will be there, robustness, and memory usage, optimized use of available memory. Question number 2, avoid taking difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, take a difference before going other operations. Taking difference of two nearly equal numbers can lead to the loss of accuracy and numerical instability. For example, if you are taking the difference of these two numbers 0.000002, then it will not be that much accurate, and this will lead to the loss of accuracy and numerical instability, especially when dealing with the floating point arithmetic. This is because the difference between two nearly equal numbers can result in very small number that may lose due to the limited precision of floating point arithmetic. So we can avoid this by using alternative formulation of the problem, or we can avoid it by taking difference before doing other operations. The question number 3 is adding or subtracting numbers start with the smallest number and works with the number in ascending order. So yes, adding or subtracting numbers starting with the smallest number and working with the number in ascending order can help to improve the accuracy and numerical stability of the calculation. So by adding or subtracting number in an order or an ascending order can reduce the impact of limited precision of the arithmetic one. This is because the small number have fewer digits and are less sensitive to the rounding error and large than the large number. If I round off 96, it could be either 95 or 100. But if I round out 0.0000000, so rounding off this number would be difficult because it is sensitive and have fewer digits. By working with the number in ascending order, we can also reduce the accumulation of rounding error and numerical instabilities. This is because the rounding error accumulates more rapidly when adding or subtracting large number, while small numbers are less sensitive to these errors. The overall addition and or subtracting numbers starting with the smallest number and working with the number in ascending order can help to improve the accuracy of numerical stabilities of the calculations, especially when dealing with the floating point arithmetic. Question number 4, does not formulate an algorithm that tests whenever a floating point number is equal to 0. It is recommended to formulate an algorithm that tests whenever floating point number is equal to 0 because the floating point number are not exact and their value may be subjected to rounding off. Due to the limited precision of floating point arithmetic, it is difficult to represent certain number exactly, including 0. This means that even if two floating point numbers are arithmetically equal to 0, their representation in memory may differ due to the rounding off error. Question number 5. Third condition problem is normally due to the improper formulation can be eliminated by carefully reformulating the problem. A practical way if detects suspected ill condition is to alter the parameter by small amount of observed by their efficient effect on the solution. This statement is partially true. The third condition problem can be due to the improper formulation, but it can also be due to the natural problem of itself. The third condition means the smallest change in the input of parameter of a problem can lead to a large change in the output of solution. This makes problem difficult to solve and accurate and can lead to the numerical instability. The third, ill condition. The ill condition problem makes problem difficult because of it cannot be accurate as because of the rounding of the digit, and this can lead to the numerical instability. One way to suspect the ill condition is indeed a alter parameter by small amount of observed by their effect on the solution. This is known as the sensitive analysis. By analysis, the sensitive of the solution to change the input parameter, we can determine where the problem is well conditioned or ill conditioned. If the solution is highly insensitive to the small changes in the input, then the problem is likely to be the ill condition. However, the simple alterating parameters and a small amount may always be enough to eliminate ill condition. In some cases, a careful reformation of problem may be necessary to improve its conditioning. This may involve changing the formulation of a problem and introducing additional constraints to assumptions, or using a different numerical method or algorithm. Therefore, while detecting ill condition through sensitive analysis is useful first step, addressing ill condition may require more thoughts analysis, more through analysis and reformation of problem. In this true and false question, there are guidelines and processes are given which are commonly used in numerical computation and algorithm development. These processes and guidelines aim to improve the accuracy and stability and efficiency of numerical computation and algorithms. By seeing the algorithms, we can evaluate the how many times the iteration will occur. This is for the dividing polynomial p of x by r minus where this is the algorithm, and by seeing the algorithm we can evaluate the value of iterative approach and recursive approach in the question. So here's the divided of polynomial r by r minus x minus r will be n minus 1 into n by 2, and the recursive approach will be n minus 1. This many times the function will recurse, and the iterative approach for px upon dx will be n cross n plus 1 by 2, similar to the polynomial, and the recursive relation is also similar to the polynomial.